I'd like to talk now about averaging and uncertainties. As I'm sure you all know, a very common procedure to try and get your accuracy to be greater, your uncertainties to be less, is to make repeat measurements and average them. What I'd like to talk about is how you actually calculate the effect of this in a mathematical way. So the idea would be we're trying to measure something x, and we get lots of different measurements. We get x1, x2, x3, and so on. Each of these has an uncertainty, let's say sigma x. But what we want to do is work out the average, x bar. Now the average is just 1 over n plus x2 plus x3 up to xn. So that's the definition of an average you should all know. You just add up all the numbers and divide by the number of them. But what's the uncertainty in this? Sigma x bar. Well, you can work it out just by the normal uncertainty propagation equations. The squared is going to be the sum of all these squared. So that's sigma uncertainty in x1 over n. So we remove that here and put them all over n. So the uncertainty in x1 over n is just the uncertainty in x over n. And we add them in quadrature, squared. And do it again here. Oops. It's also sigma x over n. I'm assuming that all these measurements have the same uncertainty. So you're getting the same term from each of these things, adding them all up, and you're going to have n of them. So the uncertainty in x, the average in x, is just n sigma x over n squared. So that gives you the uncertainty in the average is just 1 over root n, the uncertainty in the individual measurements. Very simple, and once again we have the root n, this magic root n that comes up all over the place. So that's all there is to it. So let's say, for example, you're trying to measure the temperature of a liquid, and your uncertainty is plus or minus 1 degree, but you make 25 measurements, so n equals 25, and if you average all the 25, the uncertainty in the uncertainty in this is going to be the uncertainty 1 degree divided by root 25. So it's going to be 0.2 degrees C uncertainty in this. So what you can see is the more measurements you make, the smaller your uncertainty in the average becomes. But because square root x as a function of x only goes up slowly, as you get more and more measurements, the gain becomes less and less. You'll always gain by taking more measurements, but the gain in going from 1,000 to 1,050 is much less useful than the gain in going from 1 to 50. So you get most of the benefit at the bottom of the curve when n is small but increasing rapidly. Once n becomes very large, you have to make very large numbers of measurements to increase your uncertainty very much, decrease your uncertainty very much. I should also warn you that this is assuming that all the measurements are truly independent. If there's any error that affects all of them the same way, a systematic error, then this doesn't apply. In fact, you can take as many measurements as you like, and if they all have an uncertainty that's the same, you haven't decreased the uncertainty at all. This commonly fools people. But if the measurements really are independent, the uncertainty in the mean is just the uncertainty of the individual measurements divided by root n.